Welcome everyone to this very short and hopefully very easy and productive session on Python. Python is one of the simpler programming languages. It is usually simple enough that you can learn it or the core of it in about 45 minutes or so. That seems too short, but I'm hoping that I'll get you started. If you feel that if you don't know programming, you don't know Python, and this doesn't get you started, then I'll again do another session. Is that fair? Okay. And today, I think it will take 45 minutes, may take an hour, may take hour and a half or 2 hours, whatever it takes, but we'll learn it. Okay. So this is about introduction to Python. Baseline assumption is you don't know programming. So I'll start with absolute ground zero. It might be a little bit tedious for some of you who have been doing programming, but might help you reflect upon the foundations of what's programming. This session is obviously being recorded and it will be added to all the Discord channels, so you can review that. So just pay attention to what I'm saying. When we talk about programming, what do we mean? See, when we take, for example, a drill and we add a bit to it, and then we do some carpentry or something like that, or drill a hole in the wall, or put a screw through wood or something. The drill, its behavior cannot be changed. Right? It is born with a purpose, and that is the only purpose it can fulfill. On the other hand, a computer, what we call computer, this was actually, it has a very interesting history. It goes back to Charles Babbage and to Ada Lovelace. It's a very interesting pair, the history of it. Way before there were even vacuum tubes, way before there was any semiconductor, hundreds of years before, Charles Babbage realized that instead of using a mechanical calculator the way it used to be, what if we use gear systems, and through clever gear systems, we build a computer that could be adjusted to do a whole variety of tasks. Right? It was the beginning of an interesting idea that you could change the machine somehow, and then it would do not one task, but many tasks, unlike a drill. In a drill, you can change drill bits, whether you put a screw head or whether you put a drill head, but its functions are finite. Their goal was, can we do that? Ada Lovelace, who was the unacknowledged, or rather not well owned daughter of the great poet Lord Byron, she actually was very interested in all of this. So she realized that those settings that you do, the more configuration that come about, the more it makes sense to itemize, to write out the steps or the program, right? The program of execution, so that if the machine follows that, in that time, mechanical gears, this and then do this and then do this and then move the gear here and move the gear there and so forth, what you would end up with is a pretty large variety of purposes could be served with that. And therefore was born programming. So we should remember that history. As you know, here we do have one of the very powerful servers dedicated to Ada Lovelace. So, and one server is dedicated to Charles Babbage. So we'll start with that. What does program do? It says, here's a general purpose machine. We will tell it what purpose it needs to serve. Each program serves a purpose. It customizes the machine for the duration of the execution to fulfill a purpose. That's what a program is. Now, when we write program, there's one disconnect. Modern computers are not made up of gears. They have a binary language. Why do they have a binary language? The reasons are very simple and mechanical. What happens is people were creating vacuum tubes, transistors, and this is the history. It's really worth learning programming from its history. And a transistor has one of two possible states. It is neither, the word transistor comes from resistor, conductor and non-conductor, conductor and a non-conductor. So for example, glass is a non-conductor of electricity, but copper is a conductor of electricity. But a transistor is a sort of the first element that switches its character from one to the other. Suppose you have a high voltage here, V, and this is the ground of us. What happens is based on this voltage, bias, B voltage, if you give it a strong enough trigger, it will let the current go through, right? So when the current can go through based on the value of B, then it becomes a conductor. On the other hand, it is a non-conductor. So it therefore exists in two states. In a way, you can say 0 for non-conductor, 1 for conductor. So people began to ask, what can we do with these things in which we can do that? And one of the first things people realized is you could create AND logic, AND and OR logic. But when you do it with transistors, you do it actually using a little bit more sophisticated things, right? Called latches, D gates, etc., etc. Those of you who come from hardware background know it. Basically, what it gives you, and the reason it's important is, it allows you fundamentally a computer in its most primitive form allows you only arithmetic operations, operation. So for example, you can do A plus B minus B, multiplication B, divide by B. Are we together? Right. Think of it, even though it's plus, but you can create little hardware pieces that can do only 4 operations, and then you can do Boolean logic. You can do A and B, A or B, right? Not A. That's all. It turns out, and this is one of the most magical things, if you can just do this much, you have the means to do arbitrary set of things with this bit of either vacuum tubes or silicon, right? These latches and so forth. You have all the necessary ingredients, but there is one thing missing. Where did those ABs come from? So this machine, therefore, in the computer, there are 2 parts. There are essentially only 2 core parts. One is called the ALU. Could you guess what ALU stands for? Arithmetic logic unit, right? That's a fancy word. At heart, a computer, in its most primitive form, the processor, is an arithmetic logic unit. But the question is, but where did those variables come from? They are also stored as transistors. So think of as little bulbs based on the binary state of the bulb, on or off, transistors glowing or not glowing. You can say I'm storing the number 7, right? So A could be 7. Let's call this register A, this register B, and then again you have a set of bulbs that can glow, and here you may have 3. And what you would do is A and B, you would load into so now that you have the registers, ALU operations can produce the result. But the moment you produce the result, where will the machine keep the result? It needs another register to keep the result. So you will have to create another register to create the result, register of bank of transistors to keep the results. In a very primitive way, that is all that computing is. So what you have is something that stores a bit of information and something that allows you to do or does operations for you. Are we together? So we would say that looking at this basic picture, we are able to say that we can, different programming languages write it in different ways, right? You can, some people write it like this, A plus B, some programming languages will write it. So this arrow signifies what happens, isn't it? C, A plus B goes to C, right? Some people write it other way around. For example, R allows you this. But the most popular family of languages actually writes in a notation that does not make sense, as much sense intuitively. It says C is equal to A plus B. Logically, it makes sense. What it means is the future value of C will be when you take A and you take B and add them. But when you add them, C is the box in which you store. Right? So this is something actually, if you get this, then it becomes easy to understand. So I say that code should be written left to right, but read right to left. Are we together? Yeah. Code always read right to left, not the way you read English. So if I read it in this direction, let us try to interpret what does this line mean. Take B, right? Take A, and then there is an operation, right? It means I'll put both of these, load them into a arithmetic logic unit, and say, go add it. But the moment it adds, it will say, okay, what do I do? Where do I put the number? And you're saying, put it in C, right? So this is, now what happens is that, so now comes an interesting concept. In all programming languages, you have a place to keep information, like a register or something like that, right? Now, the place to keep information, there are lots of places over the evolution of a computer. The register, but then there's some things called L1 cache, L2, L3 cache. Then there's memory, and then there's, of course, the SSDs or the hard disks or whatever you call it, NVMe, storage devices that you get, or it may be remote, or it may be on the internet. It does not matter. It may be wherever it is. But when it is in the computer, in the memory of the computer, and so what we will do is, for the sake of this particular example, we'll always imagine that the storage is in the cache of the processor itself. If it isn't there, it is always pulled from memory into it. If it is not in memory, then it is fetched from the disk. That's how computers work. It's called the memory hierarchy. So, but to understand programming, think that it is just a box with the ALU and storage, right? Some cache. Storage. So what happens is that storage is literally like boxes. One easy way to think of it is there are some boxes, right? What you do when you want to do A plus B, and you do, let's say that A plus B is too easy, or maybe it's a 5-digit number and big numbers, and you want to find the sum. What you do is you reserve yourself a box, right? So, and you say, I want to put the number, let's take a number 1, 2, 3, 4. I want to put it in a box, right? Then there are two kinds of programming language. One of the programming languages will say, now, what kind of box do you need? Right? We have different kinds of boxes. One for hazardous material, one for vegetables, one for electronics to keep it from breaking, right? And one for clothes, and so forth. So it is called, because, and if you think of it as things that you ship, the only difference between real world shipping in UPS or storing things in boxes and programming is, in the thing that you store is data. right? Therefore, the box, so you have to ask what type of data is it? Is it vegetable? Or is it electronic? Is it a hazardous material? Right? Which in the language of computer would translate to what is it? Is it a text? Is it a number? You see how easy, how intuitive it is. So that introduces the concept of data type. Data type is nothing but type of object you want to store in a box. Is it making sense, guys? Right? It's making sense. So imagine that you have the box data. So analogy is object type could be, for example, clothes, electronics, um, a hazardous material, hazardous medicines, etc., etc. Right? Vegetables. And you realize that each of those boxes, they require different treatment and they will have different sizes. Right? So the analogy of this is data type. Because it turns out that which we use in computers, the things, and you can only use things that arithmetic logic, a processor can handle. So for example, you can't squish an apple into a processor. It has to be only a data type. So those are numbers, text, Boolean. And then out of these are constructed characters, let's say a character text. And out of these are constructed more compound objects, right? So you can say a car is made up of wheel and engine and body and battery and whatnot, right? Yes. In the same way, you can create more complicated data structures by, it's sort of the listing. Yeah, it's sort of composed out of it. It's like sambar, right? Now there's vegetable there, there's spice there, water there, and pulses there, and so forth. So you create complex data types, but these are called primitive data types. Now comes a fundamental distinction. There are two kinds of programming language. One, say all boxes are alike. I don't care what you want to store. You give us the object, we will figure out how big it is and we'll take care of its storage. You don't care. So you don't go to that shop and say, give me a vegetable basket. So in strongly typed languages, you need to say what it is, right? So these are C, C++, Java, Rust, Scala, etc. Right? When you ask for a box, you must specify the type. You must specify the type. So suppose you have a number 3.14 and you want to store it. So remember, you write code right to left. So you say, I have a number 3.14. I need to store it, right? Peculiarly, the storage symbol that some of these languages use is equal to, because later on it begins to make sense. But in the beginning, whenever you see equal to, it means whatever is on the right-hand side of the equal to, everything, whatever is on the left-hand side of the equal to, what is the container in which you'll store everything that is on the right-hand side of it, right? So always think of it as like this. This operation just says, put it here. That's what equal to means. Are we together? Take what is on the left. Let me write it out. Take what is on the right. Take what is on the right and put it in the box on the left. That is all it is. In different programming languages, we'll do that. So in strongly typed, you will say, so then there is one thing you have to do always. You don't just get a box and create a mess, because then who knows which box has your stuff and which box has other stuff. Imagine a room full of brown boxes. We all do when we move. Don't you hate it if you forgot to label your boxes? Right? You don't know what is the kitchen stuff and what is that. So you must, one rule across all programming languages, you must have not a box, but a named box. Named box. You need to give it a name. So you can call it whatever you like, generally. There's certain rules, you can't be funky too much about it. But so long as you're thinking language, right? Language and numbers, you're doing fine. There's a fancy term for it. It is called alphanumeric. Alpha means alphabet plus number. Alphabet plus number becomes alphanumeric. That's a fancy term. Names must be alphanumeric. But then the IE, alphabet plus numbers, and then plus the underscore is given an honorary position. That too is allowed. Now, for some reason, we all decided that it is even though it's not a duck, we'll call it a duck, and that sort of thing. So you can build it. And now comes an interesting question. Is this I'll give you some names. Sally. Is this allowed according to our rules?
Yeah, hello.
This is allowed. Is allowed?
No.
No. Why? Because it's not alphanumeric, right? Some of the characters are not okay. There is a further rule in some languages that you must start with alpha and then the numeric, alphabetic letters and then numbers. So some languages, actually most languages, insist on character start. But a question arises, character in which language? Right? Because a lot of this work was done in English, there is an English bias. The languages like C, C++, Java, the alphabet for languages like C++, Java, C, C++, Java, alphabet is strictly English. Later languages relax that. For example, one of the lovely things I like about Python is, in Python, Greeks are fine, right? Now, why would you like to give Greek a special place? Because most of mathematics is written in Greek, right? That's why it feels Greek. When people say, right, I don't understand it, it's Greek. Now you know where it comes from. Right? So Python allows Greek. Actually, those of you who took my foundation class, you must have noticed that a lot of the variables that I defined in some of the Jupyter, they were Greek, theta and pi, isn't it? You remember that. So this is something, named boxes. But once we have a named box, let us call it this number. Let me call it, what would you like to call a number?
Pi. Pi.
No, don't call it pi. Pi is a reserved word in some languages. Let's call it x. Right? Let's call it x. So now it is. So now what happens is, in languages where it is strongly typed, you cannot get away by just saying, my box named x. What is missing?
Data type.
What type of box it is? For vegetables or for, right? For electronics. So you need to give the data type. So you have to say, for example, float. Now, the word float has a long history, but we need not go into. But whenever you see anything that has a potential decimal in it, float is a good choice. Float, double, etc. Different languages have different defaults. You put it this way. In weekly, there is something called weekly or scripted language. In scripted languages, by scripted means there's a technology called interpretation at runtime. I mean, you write the code, nothing happens to the code. It just sits there till it is run. So there's some technicality there. So there are two kinds of language called compiled languages. The strongly typed languages are usually often compiled. Languages. Interpreted languages. Interpreted languages, it is still compiled, but at the last minute, just in time. You have the luxury that you can write only x is equal to 3.14. Now think from and that's the word interpreter, think from right to left. If if vegetable has to be stored and at the counter, the box counter, there is a smart guy, what will he automatically do?
Put it in the vegetable box.
Yeah, he will automatically bring the vegetable box and put it there. You don't need to tell it, right? That is the point of scripted languages or interpreted languages. You say, put it where appropriate. Fortunately, Python is an interpreted language. So you see statements like this. Now comes, what do you call? Why don't we just call them boxes or containers or something like that? It turns out that there were two kinds of containers or boxes created. People in the beginning thought we need two kinds of boxes. One box was, let me use it since I'm slightly changing topic. Let me use this. This. There were two kinds of box. Oh, sorry. Even whether or not it's a vegetable box, there was a rule. One is the box sealed or is the box open? Right? So it's like letter. You know, there's such a thing as a sealed letter. What happens if you seal the letter? Whatever is in there can't be changed. That's the purpose of sealing that box. Isn't it? Right. So suppose you create a box, and after that, the moment something is put in the box, you nicely tape it and seal it. Seal box. Right? Or you can have an open box and you tell the user that use it. You put vegetable, and then if you want to change the vegetable on the number, right? Take a little bit of the vegetable out or whatever it is, you can do that. So the contents of the box, look at the contents of the box. In the left-hand side, the contents of the box are constant, isn't it? The contents of the box are fixed or constant after being given, isn't it? On the other hand, if you get an open box, I'm sorry. Right? And freedom to change things inside. What is then contents of the box are variable, isn't it? Variable. Based on what time it is and what you're up to. Right? How far along are you? Isn't it? So these two words, actually, let me write this in capital. So now some programming languages, every programming language gives you a variable box. Because what happens is when people think through things, it's just like your scratch pad. You may put something on a page, after a little while you'll erase it and want to put something else there. Right? So variable boxes are absolutely essential. Actually, I shouldn't use the word absolutely essential. Let's say that are the norm. They're not essential. They are languages that actually enforce that once you create an object, it becomes immutable. Like once you get a box, that box automatically gets sealed forever. Those are actually, believe it or not, very good programming languages. Yeah. Variables are
Necessary.
necessary, not necessary, or considered necessary. Purists would argue it's not always necessary, considered necessary. But constant boxes becomes a choice. Hey, you take the box, you do whatever you want. I'm not going to seal it. Right? Are we together? And so, for this reason, historically, whenever you ask for a box, the, the phrase variable box, a box that can contain an open box, is often called, the word that has stuck in the industry is variable. So, variable. So in English, it sounds very odd when you say, I will store the number in a variable named X, right? So I wanted to give you how these words come about. So think about it. What happens is when you mean, let us store 3.14 in a variable box that we name as X, right? What people, so this, and this three layers are actually important. I'd like to sort of dwell on it, even though it's one of the things we all, I don't know, guys, are you finding this too elementary or is it okay?
No, this is
Too basic, too basic. But go with me. You guys asked for it. Right?
it's actually good, Asif. I know Python, but the way you're teaching is really, really good. Thank you.
Okay. So when you mean, let us store 3.14 in a variable box that we name as X, what we say, so between mean and say is this. So the jargon, industry jargon that you use, store 3.14 in the variable X. Now, every language has a syntax to do this. Every language has a different syntax to say it. It's in code, right? So Python's way is X is equal to 3.14. So now we should always read this backward. Whenever you see code in the beginning, whenever you see a statement, these statements are called, and jargons, like our field is replete with jargons that makes it hard for others to understand. It reminds me of the famous biblical story. Do you guys know the word shibboleth? Shibboleth? Okay, so there was a tribe of people, right? And they were under threat. Right? And then they had their own code words. So then an outsider came and pretended to be one of them to spy on them. But the trouble was, he didn't know how to say the word shibboleth, right? So he said shibboleth, shibboleth. And they all knew who the guy is. right? So it's somewhat like that. Every tribe develops its own shibboleth, its own tribal language, insider talk. And in our field, the insider talk has become like this. Python's way is this. People say also is the store in the variable, or more commonly, they say assign assign, even the value they may not say, the value, assign 3.14 to x. That's what they will say. What happens at the hardware level is you are storing 3.14 in an actual storage area at runtime, an actual box of sorts, a register area of memory, whose name now becomes identified as x. Are we together, guys? Right. So we learned assignment. So now we can do, let us see what kind of code we can do. Give me a moment, guys. My this has gotten stuck. Why am I will stop one note and I will start it again. So now let us see what we can do and what we cannot do. Suppose I want to add A is equal to 10, B is equal to 15. Right? Now remember, we are writing it as equal to. What does it mean? A box named A, a variable A has 10 in it, a variable B has 15 in it. Right? If I want to add them up, remember addition is an allowed operation, we can do that. Now, how do I do that?
Placeholder. C.
I need, adding is easy. I push it to the
Placeholder.
processor, but then the processor will say, okay, where should I write the answer? So you need to give it another box. So you need to create a box, C is equal to A plus B, and this gets done, right? Now you can have other things to do. For example, you can say D is equal to A minus B, right? And then you can say E is equal to C times D. All of these you can keep on doing. But suppose you want to do, the language needs two more constructs. So now, if you understood this, implicit in it is a basic concept, progression. You read code top down, not bottom up, because the machine will do it top down, right? Implicit assumption is progression of code, progression of machine execution, and people just call it execution, is top down, right? In this order, the statements are executed. It turns out that we need two more B's to complete the whole story of programming. And any language that has only three elements, core elements, variables, all of them need variables, constants. But if you have a sense of progression, very basic rule, if this comes above this, do that first, then do this. A clear progression or order in the code is understood, and two more B's. So we'll talk about the two B's, conditional and iteration. People call it iteration, which again seems jargonish. I will say repeat.
We call it iteration.
That's it?
We call it iteration.
Yeah, call it iteration. Yeah, I call it iteration.
Different pronunciation.
Yeah. Or repetition. 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 What does it mean? So suppose I say that if A plus B is more than 20, then C should only be 20, no matter what. It should be 20 is the maximum you can have. So let's think of a rule. If adding A and B gives a number greater than, and greater than, this is a symbol that you remember from math, guys, greater than 20, then C is 20, otherwise it is basically A plus B, actual value of A plus B. Are we together? So how would we do that? All languages give you some variant of something that looks almost as simple as reading that code. So Python, for example, gives you a if. And you can say if A plus B is greater than equal to 20, C is equal to 20. Else, because you have to do the otherwise also, right? Right. Otherwise, C, else and otherwise synonyms. I don't know if any languages uses the word otherwise, but yeah, C is A plus B. So this, what did we do? What happens here and what happens here completely depend on this condition. This condition, this is called, oh sorry, no, not this whole thing. This is the condition. There's a 2 colon here. It is called the condition. Condition, it's true, right?
Yeah.
You put your condition to your friend, right? If you bring the pizza, I'll get the drinks, right? That is it. So that is exactly what you're doing. Yeah. So now let's generalize from this. Here we just did assignment, but more broadly, more generally speaking, when you do if with some conditional, do this. Let me say do something. Yeah. So what happens is it is not necessary to say else.
Okay.
You can do nothing, right? You can say if it rains, take out your umbrella. Well, else hardly needs to be said, yeah, because that is it. So do something. So this part is your basic conditional, and optional part is the else. Optional. And when that happens, do something different. So, by the way, what you do is up to you. You can do just 1 or 2 things. You can do long list of things, right? But when you look carefully, you will see that this is the basic structure. When you start reading code, read it like this. This is it. So if else is easy to understand.
Yes.
Fortunately, Python has it very simple. Yeah?
Right.
It reads like English. This. Now, what about condition? What about iteration? It turns out, for better or for worse, Python gives you many options. It gives you something called while. It gives you for. Actually, let me write little while. I'll explain it. And it also gives you some powerful constructs, which we won't go into, called list comprehension. Comprehension. Right. Consider this an advanced topic. We will do these two, while, for. Yeah. So let us take the situation. You want to add all the numbers from 1 to 100. Right? 1, 2, 3, 4, 5, all the way to 100. How are we going to do that? Let's think through that. Add numbers. Add these. So you know that you can think input is, actually if you think about it, suppose I give you the input 1 and 100. the other numbers can easily be inferred what it will be, isn't it? So some languages give you
increment factor.
Yeah. So for example, in Python, you can actually do things like, okay, you literally have a dot dot notation. Yeah. You can say one dot dot. So then it will automatically assume that. It also has something called range, 100. But be careful, when you use the range formula, something very unintuitive happens. It will only add from 1 to it will only include numbers from 1 to 99 and skip 100. So range is, that's what it is. It is left inclusive, right exclusive. Means right is excluded. So the one before that will be kept. What comes before 100? 99. So it will become 1 to 99. It is one of the things you should really be aware of. Yeah. But generally, let's take this from here. So now the thing is, what do you want to do? Intuitively, imagine that you have these numbers. You want to pick a number. First, you want to create a bin. You want to create a box to keep track of the running total. What is the total so far? As you're doing it, what will you do? You will first put 0 there. Then you will go to the first number, and then you will say that total plus the first one, this arrow. Total plus this,
The count.
right? Whatever. So let's say total plus 1, and you will put it back into the total box, right?
Sure.
And so that you say that is an assignment operation, and weirdly it's written like this, which all mathematicians will disagree with. How can something be something plus 1, right? But this is the way programmers write it. So that is the reason I interpreted it for you, right? You get used to it if you do programming too, and it takes a while to realize that actually it is very logically, it's very illogical what we write in programming, right? The way to understand always is this mantra, that whenever you see equal to, where is that? Equal to, this picture you should always keep in your mind. That equal to in programming means something completely different from equal to in math. That's the first thing you have to remember. So when you remember that, I can say this. So now what you do, you move this thing to the second one, then third one, and you'll keep doing it to the total. So are you repeating? What are you doing? Move ahead, repeat. Move ahead, repeat. So how would I move ahead? You can say, you can do this. You can say C is equal to 1. Some number. Let me just call it location. Let me call it where your finger is.
I equal.
Right? Yeah. So people often call it index or I.
Right.
Index is, and one way to remember index is, you have an index finger. What are you pointing to? Right. So the word index is a short form of it saying, hey, I'm pointing to this now in this list of numbers. Right. So index finger points to 1, let's say. Right. Then what can you do? And you keep on moving the index till index.
Till you reach the
Till index, yeah. So we can say while index is less than or equal to 100, less than or equal to 100 effectively. And you don't write it like this in Python, but okay, let me write it simply, 101, so that it is correct syntax. While index is less than 101, why 101? Because you want to go to 100. Yeah. So then do this. What exactly do we need to do? Let's think through it. We already have a total. We create another box to keep the total. Right? We need to keep track of two things. How much is the total? And where is my finger pointing to? Right? So while index is not pointing to that, is starting with 1, I will say total
Initialize
plus, total plus index is the new total. Yeah. So the way to read it is add index to the current total and make it the new total. Yeah. Save it in the box that is total. Replace the old value with the new value. The old total value, whatever was in the total box, replace it with the new value, which is the previous value plus index. Are we making sense?
Right.
But then that is not enough. Index, now my finger needs to move forward.
Start
Right?
plus.
So we say index. Now there are shorter ways of writing it in different programming languages. But in the beginning, when you're learning, don't be clever. Like don't try this clever techniques. And don't let, for heaven's sake, cursor and other things write your code. It will completely write some cryptic. There's a shorter way of writing all this in different programming languages. So guys, does this make sense? Right. So now how do you tell that this is the conditional part, do something part? Right. What you do is in Python, every language has some notation. In Python, you sort of write indent it. If you indent the code, right, and this is unique to Python and annoys people to no extent. Right. Write indent the body of the while, and they call it the loop because you're doing it over and over and over again. You're repeating, looping. So guys, does that make sense? So you write. In other words, let me write the same code in a clean way now, briefly, and see. We first put our index finger at 1. So this is index. Initially, we put 0 in a box named total. Right? And then we say while index is less than 101, do what? First of all, leave this blank space here. Make sure you indent it. And then write total. So always remember, you always read it backwards. Take index and add it to total. What are we saying? Take the value of index and add it to the current value of total, the box total. But that needs to be stored now. So storage operation is needed. Store it back in the box that was called total. And now do the same thing for index. Index plus 1 is equal to. And thus we learned how to iterate, how to sort of iterate. Right? Now, there is a variant of this that you can do with for also. Right?
Correct.
If you're new to Python, I would suggest pick one, either while or for, and make it your favorite. Right? So many people prefer for, right? And say there the syntax gets even easier for index. And here you're looking at the range of numbers from 1 to 101. Do what? You set your total to, first of all, you need a box in which you put nothing, right? And then all you have to say here is total plus index. Actually, I need to indent it to the right. So let me put that empty box here. And this I should have indented with the for. So let me write total here. Total is equal to this for, leaving this box aside. Now I can say total index, add it to the total, the current total, and put it back in the same box that was called total, is the new value of total. Right? So when you look at it this way, there are pluses and minuses compared to the while loop. The while loop, in some sense, is more interpretable. It's easier to read when you're new. right? The for loop is more concise, more compact. So usually what happens is when you're getting used to programming, you oftentimes I recommend start with the while loop, lay it out, right? Because the code explains itself. And I like to remind people where the word explain comes from. Anybody knows what's the root of the word explain? Explain means to lay it all out on the table for people to say. So it was a metaphor, and now it became the word itself. Explain, right? So in a way, while loop is more self-explanatory. It lays it out, isn't it? On the other hand, for loop is usually more compact. And then there are things that are even more compact.
Yes.
You can do it very, very quickly, but let's not do that yet, right? So you can bring in the sum function and so on and so forth. So we learned three crucial things: variables, progression, conditional, and iteration. And here is a very interesting news. There is a result in our field that says that any structured programming language that contains all these three elements is Turing complete. What does that mean? Means every problem that can ever be solved with programming can be solved by a language that has these three elements. Means everything else in the language is optional. Those are optional embellishments, or they're conveniences that make your code more modular, more easy to read, more they're structured, whatnot. But if your language, any language that you create, gives you the capacity to write assignments, to write conditionals, and to do iterations, it can solve every problem that is solvable in code. That's a pretty big statement. And you have to, so whenever you approach a new language, here is my instinct. Over my career, I must have picked up and forgotten close to about 20 to 30 languages. But, for example, now if I write Lisp, I will make mistakes. Right? Remember it mostly, but it'll make mistakes, but because I haven't used it in a while. So how do I approach a new language? I look for it as structural elements. When you build a house, you build the foundations and the beams first. All else can easily come after, isn't it? Pillars and beams. Would you agree? The rest are all okay. Otherwise, you can just hang a tarp and still survive. It's somewhat like that. So, three necessary conditions are this. At this moment, you have a complete programming language. Your first milestone in Python is just become familiar with these three things. Now, amongst the extra embellishments, there is one thing that people have realized decades ago, that it is very essential. Whenever you repeatedly do things, you call it a procedure, a routine, or a function based on which programming language you are in, whether you're doing Fortran, C, C++ program. So it has what happens is any piece of things that you write used to, in the old days, get written on punch cards. So I did my first coding with punch cards. We had to feed it into machines. And what used to happen is, if there was a bug in your code, your machine would produce the wrong answer. The trouble is, punch cards now have punched in holes. Now you have to start all over again, and punch cards were expensive. At least in India, it was hard to afford them. Right? So what we used to do is, we would write code on paper, have our friends review it, be absolutely sure there are no bugs, and then we would put it onto punch cards. You see that, right? These days, people don't do that. People are impatient. They say, I just described my problem. Why hasn't it become code already? Right? But So the generations, I suppose the generations change and expectations change. So think of my time of punch cards. So I have written something that, let's say, draws a picture on paper. In those days, it used to be dot matrix printers. Make some picture. So they have lots of steps. Put a dot here, put a dot there, put a dot there, etc., etc. First, put these many dots at these locations. So it will be a long list of if, else, while, and statements. So what you would do is you would put it on a bundle of punch cards. And when you wanted to do it, you would literally say, where is that routine? Where is that procedure? And by asking where is that procedure would be sitting on the shelf as a stack of punch cards, and it would have a name. Otherwise, all the punch cards can be mixed up, isn't it? So that stack of punch cards, which contain a whole lot of code in it, but which you reuse again and again in programming, right? It's a very common occurrence that you have things like that, things that you reuse over and over again, a set of instructions. So the first thing in programming languages that was a movement towards structured programming was this thing that was variably called procedure, routine, or more commonly in Python, these are functions. So the biggest intuition that I can give you of function to pin it into your mind is think back to your grandpa's time or time when I was a young person, and functions used to be a stack of punch cards, right, kept on a shelf with a name. So we all agree that functions will have a name. First things first, right? It will have a name. So let us give it a name, print. And as young kids, one of the first things we did is we would try to print peculiar shapes using right? I remember once I tried to print the big shape of pi, right? Using a dot matrix printer. Print shape. Let us say we have a function called print underscore shape. Remember, underscore is considered alphanumeric, right? So you can name something with the underscore stuck in there. It just becomes more readable. And you can give it a number, let's say X. So if you give it something that print what, shape of what, you give X is whose shape you want to print, a number, let us say, right? So this is the name of a function. Now, what is inside written on the punch card is the body. So again, you do indentation and then you follow it with the body. Body, right? So you say that in your code, you use this keyword. Let me color this keyword up. Def. It is literally going and labeling that, put on the punch card collection. You are putting a label, you're defining. Def is define. But the way I look at it is just here is a set of reusable instructions that you will use again and again and again, right? So functions are, let us write it down. Functions are reusable instructions bundled up, isn't it? Think of my punch card era. A procedure, a function was literally certain number of bunches, and all of them would have instructions. It may have progression, if else, there may be a while. All of those things will be inside the body. Whatever it takes to print a shape. Are we together, guys?
Right.
But you don't want to paste the shape every time you want to print. Like I want to print the shape of 3, I want to print the shape of 5. You don't want to keep on rewriting mostly the same code. So the reusable functions provide reusable instructions and were considered the first big success in creating manageable and reusable code. Are we together, guys?
Right.
So today, believe it or not, if so now the thing is, I define the function, but how do I say, hey, give me the punch card, print shapes punch card block,
Call.
and use it? So what I would say is that at somewhere, so this will be state, but in your code, somewhere where it says print shape, let us say 7. This is called, so there's a jargon that you use is, this is called the definition. Definition. This is define, definition. Definition of a function. So you realize that definition is made up of the body. But what about this? What is this called? It is called the declaration. Fancy words. All it means is you gave a name to this thing and you told what it takes as input, isn't it? Input also has 2 fancy names. It is called argument. I don't know, maybe some people were arguing together. Or it is also called the input, which I like much more. Or it is called the parameters. Parameters, right? Argument, input, parameters. Arguments, inputs, parameters. And you can give it more. For example, if you want to multiply 2 numbers, you have to give both, right? So let's use this, and then print is calling this. So now we go through the simple exercise of defining a couple of very simple functions. Suppose I say, I need a function that does input x square plus y divided by 2. This is what it does and returns the value. How would I do that? Let us go about it. Let us say first def, we need a name for the function. We will call it quadratic, some quadratic function. So let me just call it quadratic, simply, right? What are the arguments? It needs to be given x, it needs to be given y. Def, and now comes the body. So we leave some space here. And in the body, what will we do? First thing we will do is, we will create a result. Let me just call a variable, another box to keep partial results, right? So let us say answer is equal to 0. First thing we can do is, we can start by setting the answer is equal to y, right? Or we can directly say, okay, see, we can do, then we can say answer, let us bring x square in there, is equal to answer plus x star x. We could do that. Right. And then finally we could say answer is equal to answer divided by 2. But now the question is, how do we give it back? It is saying, because it's like a function is like a box, it will return you something at the end of it, right? Return, right? So it is laying it out piece by piece, you're adding it. But now you say, well, that is rather verbose, and I can do much better. So a more compact would be def quadratic x, y, and in there you say, and this is being really clever, return x star x plus y divided by 2. And it will work, right? Then what happens is, you leave it to the processor to piece by piece bring things into the register and keep doing the operations. So sometimes you can make the code much more compact. Sometimes, one basic practice that I recommend is never do any compute in the return value. Good point. Don't do computes in the return value.
So leave it as it is and do it in main.
Yeah. So what you do is write the answer, create a box called answer, and return the answer. Now you say, well, you unnecessarily created a box, a variable, isn't it? But actually you didn't, because interpreters these days are very smart. They will actually not create a box. They will erase the box. They'll say, okay, I can do without a box and return the answer. Right? So write your code in the most readable form. There is a reason for it. Because tomorrow, code becomes very, very complex. So you may want to know, what is this machine returning? Somewhere in there, you leave the door open to print answer, print x, y, answer from this function, right? So that you can see what was happening. If was there really a bug in the code, right? And print is not really a good idea. Better still, something called logging is there, but we'll leave it. There is logging. Logging just means your print statements don't get lost. They go to a proper storage location. That's all it is, right? So it gives you the advantage or the freedom later on to intercept the return value before you return it.
Good.
Right? So guys, today we learned this boxes business, and we said programming is all about boxes and an arithmetic logic unit. Right? Boxes must have a name, may or may not have a type. Python doesn't require you to have a type. We understood iteration, we understood conditionals, and we understood functions. Guys, was it easy? Any questions so far? Any questions, guys?
There's one thing.
Have I lost everybody by now? Nobody is speaking.
There's one thing they say, when you call a function, you pass an argument.
That is it.
Yeah, and then in the function you use a parameter. Yeah, that's how.
Yeah, it's like hair splitting, right? People who have unnecessary time on their hand will do all this hair splitting nuances. Stay simple, guys. Don't try to be clever. Great programmers write dead obvious code. Mediocre programmers write clever, messy code. So stay simple. At least, well, my brain is not very big. For my simple, tiny brain, I have to think simply, then only it works. Right? So I write it like this. So guys, now here's the news. That is all the Python you need to do machine learning. Because what Python, for machine learning, AI, what happens is we just defined a function called quadratic. Their libraries, open source teams have done Herculean effort, and they have made everything easy. They have just made everything into that, stack of punch cards, that functions, routines, functions. And all you have to do, the moment you hear Asif talk for 3 hours, in the back of your mind, there should be the statement, yeah, but somebody else has done this. For me, it will just be one function call, right? So for example, you have a very complicated model that takes in a question into some LLM. Yeah. Let us say invoke, literally an invoke method somewhere in which you can give the question, and what will come out of this? Answer. So you need to save the answer somewhere. By the way, this is really valid code. ChatGPT's code is invoke method. So people give you lots of super libraries are there. Libraries of what? Libraries of functions. Yeah. Vast libraries of functions. So now comes an interesting evolutionary step. See, when we learn a language, in the beginning, we learn the syntax, the grammar of the language, the key elements, sentences, phrase, clause, etc. You have learned all that. You can write English, right? You learn. But then you go to the library and see what people have written in English or in any language, Mandarin, Hindi, Tamil, etc. And that comes as a surprise because there is a wealth of writing that has been done in each language. And you can use that. So AI, from the perspective of programming, you guys are consumers or users of the large library of functions that your predecessors in the field have given to you as inheritance. That's all it is. And this is all the Python that you need to know for AI. So go review it, go with confidence. And when people talk very jargonish thing, remember that engineers, they will say the most obvious thing in a language in which no acronym is left behind. Right? No term jargon is left behind. Right? So don't be intimate. Ultimately, code boils down to very simple things. It boils down to statements, variables, boxes, conditionals, iteration, and functions. Functions are routines. And if you have lived, I suppose, in this age of ageism, it is not a very wise idea to give hints about my age. But if you have lived like me and started coding with punch cards, yeah, to you, these routines, these functions are very real. They represent that stack on the wall in the shelf with the label. That label is the name of the function, right? Try to think, see guys, when you think of things abstract, human being has learned to reason abstractly, perhaps in the last million years. But as a biological entity, fishes, worms, everything deals with things. Every creature deals with things intuitively, right? Fishes see food, right? They see leaves, they see home. So if there is one advice I'll give you, when you see code, it looks abstract. In your mental picture, try to make an analogy to something that is commonplace to you in life, right? Make it look commonplace. When it becomes commonplace, the mind grasps it immediately. And when you help others understand your code, make it right in such clear way, dead obvious way. Don't try to be smart. Don't think, for example, that if you wrote code like this, you would be considered a newbie. Let people say what they will. But if that is what makes you feel comfortable, write it like that. Later on, you can write more concisely. But the more concisely you write code, the less comprehensible it is, right? And here is a surprise fact. People will tell you that your code will take 4 statements to execute. It's not. It is wasting compute. Actually, you're not. Today's interpreters and compilers are super smart. They don't ever execute the code you write. They execute the auto-optimized version of the code that you write. So even if you write this, actually this will be executed. Isn't that amazing? That should be a strong discouragement from writing obscure, compact code just claiming that it will be faster. So the one rule, if you read my cursor rules yesterday, you will see a rule. Now, the rule says simplicity overrides optimization. Right? First, write simple, and then only necessary optimization without sacrificing simplicity. It has to be a rule. It has been a rule with me lifelong. So do that. And I'll end with that. So guys, I said I can teach you Python in 45 minutes. It's 45 minutes. Would you agree you learned something, or it was too easy, too basic? It was too basic. You're too polite to say that. But I hope I took the fear out of you. If you think I'm telling you this is all to Python. Large extent, as far as AI artwork bootcamps is concerned, this is all you need to know about Python. You need to now become familiar with all the libraries that your predecessors have created. With the language, this is it. Anybody who has been doing Python would disagree or agree?
Yes, Asif. Totally agree.
Right, yes. And did you find any value in this little session? Anyone?
Oh, definitely, yes, Sif, like how you're using the analogies and everything, it will actually stay in the mind, and like the simplicity of the code, what you mentioned for the function, like instead of returning the complex mathematical operation as a return statement, why we have to why we have to have variable, and then we return that variable. That is actually, I have been coding and that never thought came in my mind for so long years. Like, yeah, it could be used for debugging purpose. Thank you.
Yes. All right, guys. So it was either useful or a waste of time. I have no idea. But this was the Python session.
Thank you.
We want to learn your way of telling.
Hmm?
Simple and